Modern mechanical refrigeration is very simple. The theory is merely this. The liquid refrigerant, dichloro-difluoromethane, passes into the thermal expansion valve, breaking into small particles as it passes into the evaporator. Evaporation always takes place at the expense of total heat, or BTUs, of the surrounding cargo. Here, the rapidly moving molecules pass off as free gaseous particles. From the evaporator, the warm gas is drawn into the compressor. The compressor cycle is similar to any adiabatic compression, although there are inefficiencies due to heat losses. Now, the refrigerant...
Just a second, sir. I'm afraid we're getting kind of dizzy. How about taking another tack and starting back at the beginning of this refrigeration business? For example, you haven't said a word about refrigeration really being a matter of heat. We actually use heat exchange to make cold. So we have to understand a few things about heat first. Like the law of heat flow. That's easily demonstrated in an ordinary home steam heating plant. In this steam furnace, the heat from the hot flame flows to the water, which is cooler. The water gets warm, and the heat flows from it to the cool radiator. When the radiator is warm, the heat flows out to the cool air in the room. From all this, we can see the law of heat flow. Heat always flows from warmer substances to cooler substances. This heating plant also shows us something else about heat. As the water in the boiler takes on or absorbs more and more heat, it finally changes to steam, a gas. This is boiling or rapid evaporation. Then, in the radiator, as the heat from the steam flows into the room, the steam cools until it finally changes back to water, a liquid. This is called condensation. From this we see the effect of absorbing heat. A liquid turns to gas. We call this evaporation. And the effect of losing heat. A gas turns to liquid. We call this condensation. Now, it's important when dealing with heat to know how to measure the amount of heat that goes into or comes out of a substance. Measurement of the amount of heat is something entirely different from the measurement of temperature. To demonstrate this, let's put a pound of water in each of 2 beakers. The water in one beaker is fairly warm. In the other, it's fairly cold. Now, let's heat the water and let each beaker absorb just enough heat to raise the temperature of each pound of water just 1 degree on the thermometer. It takes the same amount of time for the water in each beaker to go up 1 degree. This shows us that no matter what the original temperature of the water is, it takes the same amount of heat to raise the temperature 1 degree. This amount of heat is taken as a standard unit with which to measure the amount of heat in any substance. It is called a British thermal unit, or simply a BTU. Each beaker of water has absorbed 1 BTU. So we see that 1 British thermal unit is the heat required to raise the temperature of 1 pound of water 1 degree Fahrenheit at sea level. The BTU is used to measure the amount of heat in any substance, solid, liquid, or gas. Of course, as the water cools to its original temperature, it gives up 1 BTU. Now, let's heat the water again, and this time we'll add enough heat, or BTUs, to make it boil. As we all know, water boils at 212 degrees Fahrenheit. After the water boils, we can keep on adding BTUs, but the temperature of the water will stay at 212 degrees. It won't get any hotter. What's happening to this extra heat? It's being used to make the water change to steam, a gas. Let's see how it looks in a diagram. We'll use a thermometer to represent the temperature of the water. Along this line, we'll show the BTUs being added. Now let's see what happens. Suppose we start with the water at a certain temperature and containing a certain number of BTUs. As the water absorbs BTUs, its temperature goes up until it finally boils at 212 degrees. But as the water absorbs more and more BTUs, its temperature stays the same. This extra amount of heat that does not affect temperature, but which we have to add to make the liquid evaporate and become a gas, is called the latent heat of evaporation. If we cool the gas, it has to lose the same number of BTUs before it will change to a liquid. This is still latent heat, but this time it's called the latent heat of condensation, since we're condensing a gas or changing it to a liquid. Water can change to a gas at ordinary temperatures. If we just let water stand, it will eventually evaporate. That is, turn to a vapor or gas. But it will take longer because we're not applying much heat to it. It gets the latent heat needed for the change out of the air or anything else that is near it. So we see that latent heat is the number of BTUs that must be added to change a liquid to a gas, or taken away to change a gas to a liquid. It is this property, the ability of a substance to absorb or lose its latent heat as it changes from liquid to gas or gas to liquid, that is the basis of a refrigeration system. Up to now, we've seen the law of heat flow, effects of heat, evaporation and condensation, what a BTU is, and what latent heat is. Now let's see if this makes our story easier to understand.
Yes. Well, the liquid refrigerant, dichloro-difluoromethane, passes through the thermal expansion valve and into the evaporator, where it absorbs its latent heat of evaporation. Then to the compressor. From the compressor, the gas, now having absorbed heat during compression, passes into the condenser. This is an ordinary, familiar immersed tube type with water as the coolant.
Beg pardon, sir, but can't we start with a simple refrigeration system first? And it can be simple. For example, suppose you wanted to cool the water in an ordinary canteen. All you have to do is wet the canvas cover thoroughly, then hang the canteen up where the air can circulate around it. Now here's what happens. As the moisture in the canvas cover evaporates into the air, it absorbs its latent heat of evaporation. Now where does it get this heat? You guessed it, from the water inside the canteen. As long as evaporation continues, the water in the canteen will stay cooler than the air outside. You're using the moisture in the cover as a refrigerant. You could cool the water faster by using alcohol as the refrigerant. It's just possible that you got a shot in the arm in the Navy, so you know how cool alcohol feels when they swab it on your arm. That's because it evaporates more rapidly and at a lower temperature than water, and absorbs more latent heat. Or you could cool the water even faster by using a substance called Freon, which evaporates so easily that it has to be stored under pressure in a tank like this to keep it liquid at all. Freon evaporates at a temperature far below the freezing temperature of water. So we can use the latent heat that Freon absorbs when it evaporates to freeze water or to keep food cold. When Freon is released from the tank,